Hyperplanes are just a way to generalize the idea of planes. And to kind of motivate this definition, we'll just take a step or two back. In two dimensions, so in R2, we could, we usually don't, define a line which is one-dimensional as given a point P0 and a vector, we'll just call it AB, the set of all points P such that AB is orthogonal to the displacement vector from P0 to P1. From P0 to P, or not P1, just P. So it's orthogonal to that, meaning that dot product is 0. We almost never write it this way, but let's think about what this is saying. This is saying, in practice, this would be like saying 3, 4, and let's say P0, so this is our AB. Let's say P0 is 1, 2. Well, this displacement vector would be given by x minus 1, y minus 2 equals 0, giving us the line 3x minus 1 plus 4y minus 2 equals 0, which I think if you rearrange, you'll be able to convince yourself is in fact a line. Okay. Now, much more familiarly, in R3, we can define a plane which is two-dimensional as given a point P0 and a vector. I'm just going to draw dot, dot, dot. The difference is that our vector is now ABC. It is the set of all points such that A, B, C dot P0, P equals 0. And this is our equation for a plane, giving us something like, if this was 3, 4, 5, if 3, 4, 5 is our vector ABC, and we'll say 6, 7, 8 is P0, we'd get the plane 3x minus 6 plus 4y minus 7 plus 5z minus 8 equals 0. And basically in Rn, we can define a hyperplane which will again just be one smaller dimension than our space, which is n minus 1 dimensional, as given a point P0 and a vector. We'll just call it x at this point because we don't have an arbitrary number of letters, but a vector in Rn. Then the set of all points, blah, 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 P such that x dot P0, P equals 0. And it would just generalize this formula further. Okay, so that's what a hyperplane is. Why do hyperplanes matter? Well, it turns out there are actually real-life examples that use hyperplanes in application. One of those examples is called the budget hyperplane, and it's an application in economics. So I'm going to give a slightly simplified example of what this means. But basically, what happens is if I have some money, we'll say $D, and I want to buy N goods uh, in different quantities. Then, if I take a vector giving me the price of those goods, of each good, so this is the price of each good, and dot it with the amount of each good that I want to buy, I can, as long as that dot product is less than the amount of dollars I have to spend, I'm able to buy those goods. In fact, we call the hyperplane given by P dot X equals D, we call this the budget hyperplane. And I should also say, because this is part of what I'll ask you to do, the amount of each good is also called the commodity bundle. Commodity bundle. Okay. So we have that. Let's do an example. So let's say I have 5 different goods and their prices. Say my price vector equals 10, 15, 20, 25, 30. And let's say I don't know how much I want to buy of these yet. So my commodity bundle will just be given by X1, X2, X3, X4, X5. Then my budget hyperplane, if I have $100, my budget hyperplane, we'll scroll down a little bit, is 10, 15, 20, 25, 30, dotted with X1, X2, X3, X4, X5, and it's the dot where that dot product equals 100. And we can rewrite this out as 10x1 plus 15x2 plus 20x3 plus 25x4 plus 30x5 equals 100. And basically what it's saying is, as long as I have a set of positive values, x1 through x5, that satisfy this equation, I can afford to buy that combination of goods at the given price vector. So that's all well and good, but when we were talking about hyperplanes, we wanted an orthogonal vector and a point. So what's our orthogonal vector and point? Well, the orthogonal vector is just going to be our coefficients. In fact, the orthogonal vector is our price vector. So that's nice and easy. But we need to do a little bit of work to find a point. Thankfully, it's not too much work. For the point, one way to do that is just set everything except for one variable equal to 0. So we'll set x2 through x5 equal to 0. And what's left? Then we get 10 x1 plus a whole bunch of things that equal 0 equals 100. This implies that x1 equals 10. So what that means is that I can write my equation, I'll rewrite it a little bit, as 10 x1 minus 10 to represent that we have a point at 10 plus 15x2 plus 20x3 plus 25x4 plus 30x5 equals 0. And you'll see these are the same thing. If I distributed this out and moved the 100 over, I'd get back to my original equation. And what this tells me is that the point 10, this is secretly x2 minus 0. We just don't write that. Similarly, x3 minus 0, x4 minus 0, x5 minus 0. The point 10, 0, 0, 0, 0 is on the budget hyperplane. So in this case, we have a hyperplane, which is this thing we can't really visualize, which represents the different combinations of quantities of goods we can buy. And we were able to write it as a dot product, and we were able to find an orthogonal vector and a point on this hyperplane. So there you go. There's an example of where we can actually use hyperplanes.